I'd like to thank organizers of this workshop, David, for very kindly inviting me, and the conference I enjoy very much, and the program in general. I attended several events, and I think it's a very successful program this year. Now, so the work I'll be talking about is done together with Brenda Quinn, who is a postgraduate student at Warwick and sitting there on the back listening to this talk. And on related issues, we collaborate also with Colm Connaughton, and I guess we have special thanks to him because actually he helped Brenda a lot with debugging numerical code, which made these calculations possible. So the model straight away I'll introduce, very familiar to people in this room, beta plane quasi-geostrophic model. Of course, this is kind of a standard picture of zonal flows in Jupiter that goes with it. So it's, in some sense, a minimal model to describe things like that. Condensation into zonal jets appears within this model because of presence of beta effect. And of course, it's a very well studied model. And can we say anything new and exciting? And I guess you know the answer.
But also correct.
Okay. So I leave aside issues how correct it is. It is very interesting. It's a very interesting model. It's almost as interesting. It's as interesting as a 2D Euler equation in Navier-Stokes, and even more so because of beta term introducing new things. And you will see today, I hope, by the end of this talk, that there is still yet to be learned. So, brief outline. Well, first, this will be all around some extra invariant that Sasha Balk, myself, and Vladimir Zakharov found in 1990, quite accidentally, and we reported it in a board conference. If I don't know, perhaps some people who are here know in 1990 there was a board conference in Perm. This one wild conference you don't forget. I guess anybody was here? Vladimir. I remember Marie Fash, but she's not here.
Zakharov was here, but he talked mostly about ocean waves.
Yes, well, no, this is something we did on Rossby waves and drift waves that was subject to my PhD thesis exactly the same year. Okay, now with this extra invariant, I will tell you about Fjordov argument for these three invariants and what the consequences are. That was also discussed there in some way. So now I will see how all that means that cascades are anisotropic and predict formation of zonal flow. And basically, the most of today's sort of the new stuff is numerics that we do. And to check these ideas, check conservation of this new invariant, what we call zonostrophy, just for the because it forces zonal flows to form, and really directly check where do these cascades go. But I start with some very brief overview of well-known things. Fjordov argument for 2D turbulence. Just because I just discovered that everybody means his own thing by Fjordov argument. And I think the simplest way it is ad absurdum contradiction argument, where you assume that well, let us assume energy, turbulence is excited some intermediate scale, which is separated at dissipation scales k minus at small k, at k plus at large k, by large non-dissipative ranges. And let's now, then there will be production rates for the entropy energy will be related by this sort of estimate. And then if I assume for the moment that energy is dissipated here at the rate comparable to its production rate, so at least some non-vanishable part of energy is dissipated here, I immediately arrive at contradiction that I will dissipate this much of entropy because of relation between energy and entropy via k squared, this much, which is much greater than it is produced at the forcing. So you cannot dissipate in steady state more than you produce, and therefore this is a contradiction, and therefore most of energy can only be dissipated in the opposite side. And the similar thing goes vice versa for the entropy. That shows that it cannot be dissipated here and goes here. So I only reproduce that because it's one of the main subjects of this talk, to actually use theory of argument, kind of straightforward generalization for something else. Now, well, okay, that's another well-known thing, crossover in between of waves and eddy motions. So equating the linear and nonlinear parts of the equations gives us Ryan scale. And if we want to go actually take into account anisotropic nature of linear and nonlinear scales, then we actually have, it's not just one scale, it's the whole curve in k-space, kx and ky, which is commonly known as a dumbbell curve or lazy 8. So introduced, well, lazy 8, Greg Holloway, 84, Vallis and Manshoot, 93, called that dumbbell. Okay, and so essentially, as I said, it separates strong turbulence, eddies, where beta effect is not important outside of lazy 8. And if we force somewhere very far from it, at an even bigger wave number, then we have more or less Krajichnan's isotropic inverse cascade as it would be without any beta. When then we come close to that and a boundary, and then the cascade becomes anisotropic. So there are, of course, some understanding that this is much harder for weak wave-dominated dynamics to carry cascades, and therefore there will be significant slowdown, although not really halting of the cascade. There will be slowdown. It will be slower cascade. So it might try to want to get past that curve, or, on the boundary like that directly in strong, along this remaining strong, or it actually it seems that it does penetrate in here too, and cascades via triad wave resonances. So and now another well-known thing is that if it is triad resonance dominated inside, say, the dumbbell, and with additional assumption of random phases, which is quite physical, phases tend to mix, so then we arrive at a closure for the spectrum of, wave action, which is energy spectrum divided by frequency. And so the equation Longy, Higgins, and Gill in the context of Rossby waves. So, you see here characteristic for wave kinetic equations, delta functions in k and omega, which is describes here triad resonant interactions. Now, it is precisely that this equation that conserves exactly possesses exactly an extra quadratic invariant, right? So this is extra invariant with respect to usual ones, such as energy, the entropy, momentum, okay? And this Rossby wave system is unique. It's not known any other system where such an additional invariant exists so far, not been found. Okay, so we originally stumbled on it, quite accidentally, and found it in two limiting cases: ky much greater than kx, so kind of zonal scales, and also k rho much less than 1, so the rho being deformation radius. So then, as I said, it's exact for kinetic equation. What's interesting for any interaction coefficient, actually, if you're not thinking about Charny kind of equation, but this one scalar nonlinearity introduced by Petviashvili in plasma context, then it will be conserved too. So it's really a property of resonant interactions. Now, because kinetic equation implies conservation of, implies small nonlinearity, and in addition to small nonlinearity, a statistical assumption about random phases. So it is not too clear what is the minimal conditions for this invariant actually to be valid. Okay, you can say it's adiabatic invariant. In original dynamics, it has to be conserved. The better, the closer we are to that assumptions under which kinetic equation works. But maybe it works better than that because it hasn't been actually verified based on the dynamical equation rather than kinetic equation. What are the conditions and what are the errors of conservation of this invariant? And that's why it's important for us to go and calculate dynamical equations and see what this kind of quantity is doing there. Now, in the same place, Fjordov argument was used to see the cascade directions. It was actually working for ky much greater than kx, where this invariant is positive. And you know that it's important for integrals to be quadratic and positive to use Fjordov argument. But in this case, it was not really positive. And moreover, Sasha Balk soon thereafter generalized it to a general case of k with respect to deformation radius. And it was also not positive. Okay.
So it is an invariant, but it's not polarizing.
That's right. So like, for example, like momentum that can change sign. So it's you can't use this contradiction argument. It won't work. You can use it one way. Yes, that's right. But for restricting direction of cascades, it won't restrict direction of cascades of positive invariance. Now, so using Fjordov argument would be problematic for that case. Now, very recently, we actually just checked what would happen to that general expression if we take the opposite limit. And that's, as I understand, the most important limit for sort of in applications, right? So and turns out it's positive. So I guess it's the first place where publicly you can see this expression presented right now. So this is how it looks. Okay, this is a Fourier transform of string function. So this is the invariant. Okay, so it's positive, and that this is good news because we can now use Fjordov argument, which we do here. And so, by the way, just for those who saw this expression, such as it involves quite involved expression with arctangent functions and stuff. And to get to this one, you actually have to go to a fifth order of Taylor expansion of that expression. Quite because up to fifth order, it's just the combination of known invariants, energy and entropy.
Excuse me, you have k rho small compared with the one at the top, large compared with one At the bottom.
Right now, k rho much greater than 1. So
Does the invariant exist in this situation?
yes, so this is the invariant. Yes,
Doesn't that mean it's simply non-divergent barotropic dynamics?
exactly. So in fact, the equation I wrote over here already in this. So it does not have this rho term over here, right? So that.
No, assuming ky much bigger than kx.
Not right now. No.
No.
That's it. I'm totally general in this respect, and but my deformation radius is infinite. And okay, so the well, first kind of obvious statement that three cascades cannot be isotropic, right? Because you can't share two-dimensional K space into three sectors in isotropic way. And so let's now, well, to kind of do this standard, well, sort of straightforward generalization of Kraichnin's inertial ranges. In this case, I'll have to produce turbulence around some scale K naught and surrounded by large inertial non-dissipative regions, which is kind of like a ring in this case, and dissipated far away from this scale. So either at large, very large K, or close to the axis, where one of the wave number components equal to 0. Of course, in real systems, that doesn't occur. This is just to obtain, to apply in the most straightforward way the same Fjordov argument. And then, if you remember, Fjordov argument that as I put it, the boundary where energy and separates energy and entropy cascade is determined by the densities of this invariant equal one to another. So in this case, it's k equal to 1, or k equal to k naught, right? So one goes to k much greater than k naught, another can go to k much less than k naught. In this case, now we have third invariant, and we have three boundaries. We have three lines in K space. We equate these densities of invariant one to another. And by the way, for the purposes of this argument, this is just k squared, because it's bounded by from above by 5k squared and below from k squared, right? So I just can, for this Fjordov argument, think of it as k squared.
So sorry.
Yeah.
Why is convergent this integral?
Pardon?
What about logarithmic divergence of this integral?
That divergence, well, it really depends on what you have here, how this function behaves, decays, yes. So now, so these boundaries are correspondingly, well, the old one we already know. Well, actually, because it involves k and kx, we are in k space, we should be on the axis, its best representation is kx and k, rather than kx and ky. So here we produce our turbulence, and this boundary is k equal to k naught, you already know, between energy and entropy here. So energy cannot go there, and entropy cannot go here. But now boundaries between this one and that one, and that one and that one. So this one and this one gives correspondingly kx to 1/3 line. So energy cannot go in here, and zonostrophy cannot go in here. And for the entropy, correspondingly kx to 1/4. So entropy cannot go here, the zonostrophy cannot go there, right? So we have three sectors, and so for the entropy to large k and a little bit anisotropic, for this, and you see that the presence of this new invariant bites away a whole big region in Fourier space and pushes energy to zonal scales. Now, and this is something we can check numerically. So numerically, we are going to do the following setup. Okay, so use pseudo-spectral method with no dissipation. Instead of a forced dissipative situation, we are going to put initial condition around as a Gaussian function. around some scale k naught with some thickness k star, okay, with phases being random within this initial condition, right? And then we are going to evolve the system. So the spot is going to start spreading according to evolution of the Charney equation. And we will see, and what we will be looking at, conservation, of course, we will check off this invariance, okay, first thing. But second, we will be looking at the cascades. We're going to characterize them as centroids of energy, okay, so the energy containing scale, which is happens to be integral scale. Okay, so similar for the entropy and the zonostrophy.
Question, Sergey?
Yeah.
So psi is the stream function, or now it's something else?
Psi is the stream Fourier transform of stream function.
Okay.
So here is the first result, numerical result. So this is for the nonlinear to linear term. Well, roughly speaking, it's k naught where we put initial turbulence with respect to Rhine scale. So squared parameter. So we are quite well within the dumbbell shape, we're inside in the wave-dominated region. Okay, we expect wave turbulence there to be quite good. Now, so because evolution is slow for wave-wave interaction, weakly nonlinear, we then choose to plot another quantity, psi squared, which is not expected to be conserved, because we don't want to check conservation for something that's not evolving, right? So all quantities are going to be evolving very slow. So this is that non-conserved quantity. You see it evolved quite well, just for comparison. So then energy is conserved very well. Entropy decays slightly. Mind you, this is only 0.8, right? This is numerical dissipation. We don't really have any dissipation introduced there at all. But you see that this extra invariant zonostrophy is doing pretty well. It's really conserved brilliantly here. So I remind you, okay, take square root. We are kind of halfway within the dumbbell, right? So we're kind of right in the middle, not too weakly nonlinear. Okay.
You solve numerical kinetic equation or full
No.
equation? Full equation.
Full equation.
Is the equation supposed to conserve energy and entropy?
Equation conserves energy and entropy. Yes.
Okay, a spectral code, 2D spectral code, properly resolved will conserve those quantities exactly.
Correct.
Unless you move things to high wave number and you have a spectral cutoff where you're taking entropy out at the large wave number.
Exactly. So and if you have some issues with discretization, time discretization, well, this is very slow evolution. This is weakly nonlinear. It bounces forth and back, for a long time. That's why. So this is numerical failure. This is failure of numerical code. This for non-conservation of entropy. Mm-hmm.
But in general, zonostrophy, as you wrote in the limit, is not conserved in general. You have to have.
We don't know. So it's kind of we think it's adiabatic invariant, but we don't know whether it's enough to have small nonlinearity or some statistical properties as well. That's why we do numerics.
One more picky question, sorry.
Okay.
I just wondering, did you look at another quantity with the same dimensions as zonostrophy as a test? I mean, something because you have that 1 over k squared
Yeah.
pushes it to low wave number.
We can check that. I mean, we didn't.
Okay, that would be more
I'm pretty sure that wouldn't be conserved, but this is easy to check. Right, now let's me really move on quickly. Okay, so but because I have still some important view graphs. So here's the main sort of result, you could say, right? So these are the centroids of energy, entropy, and zonostrophy. So these are the sectors. Energy was supposed to go here, and you see it kind of, well, first of all, you see that they do as predicted. They are by the Furtov argument, right? Now another thing you can see that energy actually goes within this sector, but on the boundary of it, right? It's allowed to go on the boundary. It just doesn't. It's not allowed to go very deeply into another guy's sector. But for some reason, which we don't know why, it just goes right on the boundary, and that's prediction. So that that the integral scale actually goes along the line k equal to cubic root of kx. Okay, so now you can see that this line, that if everything would be scaling self-similarly, so more or less isotropically, right? So k is proportional to kx. So you see zonostrophy kind of tends to move almost supported on isotropic motions. Right, so now strong nonlinear run, you can see again that, well, this zonostrophy, you see originally it's not conserved, but then it levels out. And energy and entropy, so this is now, but so this is run where you essentially take square root, you are right on the border of dumbbell, okay, so that you're strongly nonlinear. And you see that this later on conservation of zonostrophy means that you become more weakly nonlinear as you proceed. You kind of enter by inverse cascade into the dumbbell, and so you're getting more weakly nonlinear even though you started with less weakly nonlinear. And that's kind of like illustrates that you don't really go along the dumbbell on the borders with inverse cascade to create zonal flows, but you actually penetrate into it mostly. Okay, now these are the cascades. You see this is much faster, much less jittery spectra. So you see again, qualitatively similar picture. So energy goes over here, although now considerations are not exact. Of course, you don't expect everything exact. Zonostrophy goes pretty along isotropic line, and also the entropy also supported kind of on isotropic motions too. It goes along this diagonal. Just one thing to say here, that if we take much weaker nonlinearity, you could think, well, okay, weak nonlinear case is simple, not numerically. It's very hard, notoriously hard to compute. You have a lot of recursion, a lot of, it's huge, it freezes over.
Strong.
Weak, it's very weak. So you lose resonances, okay? So because of discrete k-space, you start losing triad resonances. And so there is a lot happening here that, so in order for kinetic equation to work, we know that actually turbulence shouldn't be too weak. It's weak, but not too weak. Discreteness of k-space shouldn't be. Okay, let me just show you how it's frames from the movies, X-space vorticity field. So for this strong run, so you see soon it gets into kind of zonal motions. That is, so Fourier space, you start with this, it's a logarithmic scale, start with this initial condition, and very soon you see kind of developing this dumbbell, more or less, at least qualitatively. And one thing I wanted to say is that actually you see the spectra here and also on the vorticity frames, that not exactly zonal. So the most characteristic scale is actually slightly off zonal. You saw this cascade proceeds along a line where we have relation between ky and kx, right? And so I thought, of course, this model is, I don't know, probably not at all good candidate to describe real ocean observations, but I thought it would be interesting to point out that some recent observations by Maximenko and collaborators, where he pointed out that actually the striations, this is the observation of the zonal velocity, that actually these lines are not exactly zonal. So actually the zonal flow goes along the crest, goes sometimes through the crest. The velocity is not directed like that. Sometimes it exits. And this is picture in Fourier space. You see also slightly off zonal.
That time average.
Yes.
It's a time by average, but not hugely, I guess, right? So it's not.
It's actually controversial too.
Okay, fine, right. So And that's, as I said, probably has little to do with what I'm predicting anyway, right? Anyway, so well, here is the summary slide. So one thing I want to emphasize again, that actually rigorous conditions are still not known for conservation of zonostrophy, and so that could be, if good for applied mathematicians or analysts, good problem to actually problem to study. Thank you very much.
On the last point, I thought you said that zonostrophy conservation depended on having resonant triads and random phase.
Okay, look, if that's satisfied, then it is conserved we know, right? Because if kinetic equation works, that's condition for kinetic equation to work. If it works, then it's a precise, exact invariant of the kinetic equation. However, will it work if say, at weaker assumptions? I'm not computing kinetic equation, I'm computing dynamical equation, right?
I'd be surprised if it worked under weaker assumptions myself.
But look, numerically at least it does, to some extent, right? Maybe you're right, but we don't know.
Do you have a physical explanation for what it is?
It is zonostrophy, right? So one thing I can say, it's not momentum, it's not linear combination of other guys, it's not anything that I know. So Sasha Balk found its relation in physical space recently, and again, it doesn't look like anything that we know. Well,
It's not local.
yeah.
It's like an
Going back to your random phase assumption, it's clear that if you had isotropic 2D turbulence situation, it's obvious you should expect that. But here you have very anisotropic flow. What's the argument you're making? How do you justify still making a random phase argument when you're almost precisely zonal?
Yes, and that's precisely my point. I don't justify it, do numerical experiment, right? So I start with initially random phases, that's okay.
So you're hoping and it works out.
And yes, so I'm just checking how, and also I push to stronger nonlinearity and see what kind of picture, how robust is it, how it changes.
Okay.
Well, we will discuss later, but I think I know now what's the picture in terms of discrete resonances. How to combine these two ideas.
Okay, that's great.
Yeah, because this could mean that the coefficients, interaction coefficients for the big clusters will have some extra relationships. This is typical of interoperable systems. But
I will be good, yes.
Last question.
Isn't it true that if you reach zonal flow, you must have gotten there by non-resonant interactions, and they break your conservation law?
But this is what I doubt very much, because
You doubt there's zonal flow?
yes, because what I'm saying here, look, this is the kind of illustration that makes me believe the opposite. Okay, I start with strongly on border of dumbbell, right? So strongly nonlinear. And then the zonostrophy first not conserved, but then it levels out and it starts being conserved, which makes me think it doesn't go on the non-resonant border of the dumbbell, so to say, right? The usual picture people paint. But it actually penetrates into it and becomes weakly nonlinear.
Because your k to the sixth on the denominator will emphasize the inner dumbbell region, won't it?
That is another, yes, way to see it. That's right. So it cascades to, with respect. So entropy will become more strongly nonlinear because it goes to, outside, of the dumbbell. But this one, yes, that's a good point, yeah.
All right, we can just save more questions for scale.